Okay, let's unpack this. We are diving into a concept that promises just incredible speed in software development. But on the surface, it seems completely wrong for the one place that needs it most, banking. I'm talking about vibe coding.
It's a great name for it, isn't it? Even if it sounds a little, unserious. Vibe coding is this new way of working where you use a large language model, an LLM, to write code from just your intent.
So instead of writing every single function, a developer just says, I need a dashboard that scores transactions for risk in real time.
And the AI just built it. The components, the APIs, all of it.
The speed is wild. We've seen prototypes that would normally take weeks, maybe months, getting built in, a few hours. You're not focused on syntax anymore, just the vibe of what you want.
Exactly. And that is where you crash right into the banking paradox.
Right.
Because banking is all about determinism, absolute, predictable, repeatable logic. And LLMs are, by their very nature, probabilistic. They're just predicting the next most likely word.
Which leads to what our sources call derailing.
Derailing is the big risk. And in banking, it's not just a bug. A derail is a systemic failure. It's a hallucination that could lead to a violation of AML laws or a failure in KYC.
Huge legal and financial liability.
Right. Think about the determinism gap like this. You have a customer service bot that's vibe coded.
Okay.
99 times, it explains a fee perfectly, pulls from the right documents. But on that 100th time, a customer phrases a question weirdly, and the LLM hallucinates a fee waiver that doesn't exist.
Just because the words sound plausible together.
Precisely. And a deterministic ledger system just can't handle that kind of ambiguity.
So we need the speed of the vibe, but the absolute safety of the vault. The architectural fix for this seems to be something called constrained vibe coding.
That's the mission. You take the LLM's creativity, its stochastic power, and you build rigid deterministic guardrails around it. And the way you do that is with Neuro-Symbolic AI.
And this isn't just a good idea, it's becoming a requirement. The regulators are coming.
Oh, absolutely. The EU AI Act is already classifying things like credit scoring as high risk. U.S. regulators are demanding explainability, robustness. You can't just deploy a black box LLM and hope for the best anymore.
So let's get into that Neuro-Symbolic fix. Our sources use a really clear analogy here, the Kahneman framework of System 1 and System 2 thinking.
Yeah, and it's a perfect fit. The AI is designed to mimic that split in our own minds. System 1 is the neural part, the vibe.
The fast, intuitive part.
Right. It's great at pattern recognition, parsing a messy email from a customer, figuring out sentiment, drafting some boilerplate code to get started. It handles the fuzzy stuff.
And System 2 is the check on that, the symbolic layer.
Exactly. System 2 is slow, deliberate, logical. It runs on hard rules, not statistics. And this is the part you use for executing a transaction, for enforcing a compliance rule, for managing the state of an application. It's non-negotiable.
But wait, if you're building all these symbolic constraints, all these rules and state machines, aren't you just trading one kind of work for another? Are you really saving time?
That's a great question, and it's fundamental. The speed comes from what the human is focused on. You're no longer the bricklayer, getting bogged down in the syntax of the implementation.
You're the architect.
You're the architect. You're defining the logic, the business rules, the bank's risk appetite. That symbolic layer is actually much smaller. It's auditable. It's immutable. The LLM then does the other 80% of the creative, often repetitive, coding to connect all the dots.
I see. So the division of labor is specific. System 1, the neural part, might read a payment note that says dinner with client.
And System 2, the symbolic part, completely ignores that. It only cares about the hard data. Account balance, recipient ID, available funds. It validates that and executes the ledger update. Intuition for the input, logic for the liability.
To make that work, you need guardrails that AI just can't get around. What's the first one?
The first and most critical is the deterministic state machine, or DSM. The application's logic has to follow a fixed path. We see tools like LangGraph used for this. The AI can move from state A to state B, but it can't invent a state D.
So it's literally a train on a track. It can't go off-road.
It can't. It can't skip a mandatory step like two-factor authentication, just because it feels like it. And for the really high-stakes decisions, you keep the human in the loop with the maker-checker pattern.
Oh, okay.
The AI is the maker. It proposes an action, say a big wire transfer, and it gathers all the evidence. But a human checker has to provide the final cryptographic sign-off before that state machine is allowed to move to the next step.
So the human's job shifts from doing to verifying.
Exactly.
Okay, that structure makes sense. But how do you enforce this discipline when the code is actually being written let's get into the tool chain.
You have to build the rules right into the IDE. Even in a vibe coding environment like Cursor, you need to enforce discipline from the outside.
And this is where that .cursor rules file comes in. It's like a system prompt for the whole development environment.
It's incredibly powerful. It's a configuration file with hard, non-negotiable rules for the code-generating LMM. Rules like always use Pydantic models for your inputs and outputs. Or, and this is maybe the most important one in finance,
Let me guess. Don't use floats for money.
never use float. Always use decimal.
Decimal? Every junior fintech developer has been burned by that one, that half-cent rounding error that brings down a ledger.
Right. So if the developer just says, calculate the interest, the AI might try to use a standard float. The .cursor rules file basically slaps its hand and forces it to generate the code using the correct decimal object. The IDE itself becomes a compliance officer.
So you've constrained the code generation. What about the prompts themselves? You have to move prompt engineering from, a mystical art into a real engineering discipline.
And that's the job of a tool like DSPy, Declarative Self-Improving Python. DSPy is all about mathematically validating the vibe. Instead of the developer just tweaking a prompt over and over, you define a signature, the exact input-output schema, and a metric, which is your definition of success.
So you're not just asking, hey, does this look suspicious for an AML model?
No. You define a metric. You say, I need this model to achieve 95% recall on this labeled data set of suspicious activity reports. And DSPy will automatically test and refine the prompt until the LLM reliably hits that number. It gives you mathematical proof that the neural layer is robust.
And for orchestrating all these steps, especially with humans involved, the sources point to LangGraph.
Yeah, LangGraph is better for these complex workflows because it's a graph. It's built to handle cycles, like when a user fails a document upload and needs to be sent back to the start. It explicitly models those human-in-the-loop breakpoints.
Okay, this is a pretty complex stack. Let's make it concrete. Let's walk through a deep dive case study. The highest risk workflow for any bank. Know your customer or KYC.
KYC is the perfect example of a state machine. You have these clear states: collection, document ingestion, validation, risk screening, and maybe a conditional human review at the end. The LLM is just moving the data through that flow.
And at the heart of it, you have Pydantic acting as the hard brake.
It's the foundation. It's type-driven development. The LLM pulls data from a driver's license photo, but that data is immediately forced into a Pydantic identity document model, and that model has rules.
Give us that killer example of how it stops a hallucination.
Okay, so the LLM reads the ID perfectly, but the expiry date is last month. The document is expired. If the LLM tries to hallucinate and say, oh, it's probably fine, the Pydantic model's validator function, which checks if the expiry date is in the past, just raises an error.
It stops it cold.
It stops the object from even being created. The bad data never enters the system. The hallucination is neutralized instantly and deterministically.
That's a symbolic layer, just completely overriding the neural layer. Okay, but what about more sophisticated attacks? What about a deepfake video for the liveness check?
You never, ever let the LLM make a security decision like that. Its job is just to guide the user through the UI. Please turn your head to the left. The actual liveness check is handed off to a specialized, deterministic, biometric SDK. It's just another tool that the LangGraph workflow calls. The LLM handles the user experience. The SDK handles the security.
And what if it's just a simple OCR error? The LLM reads a 0 as an O.
For that, you have a fuzzy matching symbolic layer. It calculates the Levenshtein distance between what the AI read on the document and what the user typed in a form.
Which is just a score of how different the two strings are.
Right. And if the score is too high, it's a significant mismatch. LangGraph automatically routes it to a retry or manual review state.
Let's move to the second case study. Anti-money laundering, AML. This is all about high-speed data.
Totally. AML usually runs on an event bus like Kafka, which feeds a pipeline of agents. There are two layers. Layer 1 is pure symbolic rule engine.
But hard and fast rules.
The hard rules: any cash deposit over $10,000, any transfer to an OFAC-sanctioned country, it's instant, it's deterministic, no AI involved.
But the smart criminals know those rules. So layer 2 is the neural agent, designed to catch the ones who try to fly under the radar.
Exactly. The neural agent looks for unusual patterns. It does narrative analysis, so it might see the transaction note consulting fee repeated 50 times to the same shell company. That's classic structuring.
And it also uses graph-RG.
Right. Retrieval augmented generation on a graph of the bank's data. It can see if this new customer is, say, 2 or 3 connections away from a known money launderer and flag that relationship as a risk factor.
And this is key, that agent can only flag the transaction. It can't file the suspicious activity report itself. This is where the maker-checker pattern comes back in, right in the UI.
Absolutely. The AI is the maker. It drafts the whole SAR narrative, but the UI is coded so that the approve and file button is disabled. It only becomes active after the human analyst, the checker, has physically clicked open the evidence tabs.
You're architecturally forcing them to do their job, to engage with the evidence before filing a legal document.
You have to. And if the analyst rejects it, say it's a false positive, like a cash-heavy restaurant, that rejection is fed back into the DSPy framework.
As a negative example.
As a negative example, which helps DSPy refine the prompts and makes the neural agent smarter for next time.
This whole shift is fascinating. If code generation gets this fast, the bottleneck isn't writing code anymore. It's verification and security. How do you actually trust what the LLM wrote?
And this is where we get into some really interesting tools. For something super critical, like interest calculation, unit tests aren't good enough. They only check the examples you thought of. You need formal verification.
Which uses symbolic logic to mathematically prove the code is correct for all possible inputs.
That's it, exactly. You use a tool like Crosshair. A human writes a contract for the function, like a post condition that says return equals 0. Crosshair then uses a solver, like Z3, to explore every single possible valid input.
Not just a few tests, but all of them.
All of them. And it proves, with mathematical certainty, that your function will never, under any circumstance, return a negative number. It catches edge cases the AI might have generated that a human would never think to test.
That feels like the ultimate guarantee.
It is. And another key guardrail is separating your security policy from the application code itself. That's where policy as code with something like Open Policy Agent or OPA comes in.
Why is that better than just having the AI write the security checks?
Because security policies change all the time, and you can't have an LLM misinterpreting them. With OPA, the security team manages the policies in a separate, immutable layer written in a language called Rego. So even if an attacker tricks the LLM into trying to create a new admin user,
The OPA layer, which is totally separate, just looks at its own rules and says, nope, you're not allowed to do that, and denies the request at the infrastructure level.
the application's intent doesn't matter. The policy is law.
And the final step before you go live?
You red team it. You unleash another AI, an attacker agent, that is specifically trained to find vulnerabilities. It automatically probes for SQL injections, for ways to bypass the KYC state machine. Only when the app withstands that is it ready.
So with all this in place, what happens to the job of a software developer?
It completely changes. You're no longer the bricklayer, focused on syntax. You become the architect. Your job is to define that symbolic layer.
You're defining the Pydantic schemas, the Landgraph state machine, the OPA policies.
You're building the tracks. The AI is the engine, the code filler, that runs at incredible speed, but it runs strictly within the tracks that you, the human, designed and certified.
And this all has to be governed properly.
It has to be. The AI governance board or some equivalent has to own that symbolic layer. Any change to a Pydantic rule or a state machine definition needs multi-person sign-off. You have to ensure the institution's risk appetite can't be overridden by a probabilistic vibe.
This has been an incredible deep dive. It really feels like vibe coding and banking stability. They aren't mutually exclusive, after all. This neuro-symbolic architecture really is the bridge.
It lets you get the speed of the LLM, but with a high assurance of deterministic tools. For any mission-critical system, it feels like the only way forward.
So if you're out there looking to bring this revolution into your own regulated world, here's the final checklist. Enforce Pydantic for data integrity. Adopt Landgraph to model your workflows. Use OPA to separate policy from code. Verify your most critical logic with tools like Crosshair. And always, always keep the human in the loop with that maker-checker pattern.
And remember this. The risk of your system derailing isn't mitigated by slowing down the AI. It's mitigated by building stronger, mathematically proven tracks. The new measure of a perfect banking application is whether the human architect has made it impossible for the AI to ever drive off-road.